Welcome back, Physics 30. So we started off the section 26-1 Galilean Newtonian Relativity. We looked at the first part here. Let's look at the second part here. So since neither F, M, nor A changes from one inertial reference frame to another, Newton's second law, F equals ma, does not change. Thus Newton's second law satisfies the relativity principle as well. The other laws of mechanics also satisfy the relativity principle. The laws of mechanics are the same in all inertial, again, at rest or moving with constant velocity frames, and implies that no one inertial frame is special in any sense. We express this important conclusion by saying all inertial reference frames are equivalent for the description of mechanical phenomena. No one inertial frame is better than the other. A reference frame fixed to a car or on an aircraft at constant velocity is just as good as one fixed to the earth. When you travel smoothly at constant velocity in a car and an airplane, it's just as valid to say you are at rest and the earth is moving as it is to say the reverse. So one thing that common experience, if you're traveling in your car going at a constant speed at 100 kilometers per hour in a straight direction, of course you know you're doing that. You know that you're maybe moving 100 kilometers per hour west. But you could have just said, and maybe when you're a kid you look out the window, you see everything moving backwards. It's just as important to say that, well, the trees are moving 100 kilometers per hour east with reference to me. And if you were to tape up the windows, have a really smooth surface, have the car running at rest or have the car running at constant speed, you'd have no way of determining whether you are moving or not. So that's this next point. There's no experiment you can do to tell you which frame is really at rest and which is really moving. So when you're going 100 kilometers per hour west in a car, or if you're at a standstill and that car is still running, you would have no way of determining whether you are moving or not. Whether you're at rest or already moving at constant velocity, laws of Newton's laws still apply there. You'd have no way of determining whether you are moving or not. Thus, there is no way to single out one particular reference frame as being at absolute rest. And of course, right now you're sitting in your chair likely, thinking you're at rest, but guess what? The Earth is actually rotating. It's also moving around the sun. Our solar system is moving. Our galaxy is moving. So even though we are actually moving, we perceive that we are at rest. We can't, once again, no experiment can determine which is really moving and which is at rest. Now, a complication arose, however, in the last half of the 19th century. Maxwell's comprehensive and successful theory of electromagnetism predicted that light is a wave, an electromagnetic wave, and furthermore, his equations predicted that the velocity of light is 3.00 times 10 to the 8 meters per second in a particular direction. And this is what was measured. The question then arose, well, we have that, and there's a video coming up that I'll show you. What does that mean? In what reference frame is light 3.00 times 10 to the 8 meters per second? So what is the reference frame? It is assumed that light would have a different speed in different frames of reference, just like balls, coins, coffee cups have. For example, if observers would travel on a rocket ship at a speed of 1 times 10 to the 8 meters per second away from a source of light, we might expect that the light would be slowed down by that movement, but Maxwell's equations didn't have a provision for relative velocity. It just simply said, no, light is 3.00 times 10 to the 8 meters per second, which seemed to imply that, hey, there has to be some reference frame, because what reference frame is this referring to? So back in Physical Science 20, you discussed that waves travel along water, along ropes, along strings, and of course sound waves, you can hear me talk because the air molecules are vibrating your eardrum, sending a signal to your brain. So waves back in Physical Science 20 need a medium, and light is an electromagnetic wave, so it must need a medium as well too. And it can't be air because light travels across space, which is a vacuum, all the air is out, so there has to be something there to make light travel. 19th century physicists viewed the material world in terms of the laws of mechanics, so it was natural for them to assume that light too must have some kind of medium. They called this transparent medium the ether and assumed it to permeate all space. Okay? So ether, it was therefore assumed that the velocity of light given by Maxwell's equations must be with respect to the ether itself. Scientists soon set out to determine the speed of the Earth relative to the absolute frame, whatever it might be. A number of clever experiments were designed. The most direct were performed by A. Michelson and E. W. Morley in the 1880s. They measured the difference in the speed of light in different directions using Michelson's interferometer. They expected to find the difference depending upon the orientation of the apparatus with respect to the ether. So I did give you a handout dealing with this. So this part right here, just simply highlight section there. So the interferometer, and the video I'm going to show you after this does a really good job of illustrating this and showing what they did. Basically, if we look at the interferometer, we have a source of light. It's shot across in this direction. Here we have a mirror. It's not like a regular everyday mirror. It's not silvered as much, so that some light is allowed to pass through and some light is reflected. So it's referred to as a beam splitter mirror. So we have a light source, we shine it on the mirror, some of it will be reflected and be reflected off this mirror, come back. Some of it breaks on through, hits that mirror, comes back. These distances are equal and the speed of the light is equal in both directions, then they both would be reflected back. Both arrive back at the mirror, and it's silvered on this side too, and reflect here. So that's what basically the explanation here is. Now, if there is this thing called ether that light travels through, orientating this differently in the Earth would cause different movements with the ether, so we would expect that light would not be the same speed in particular directions depending upon how we orientate this apparatus. And then the video you're going to see after this does a real good job showing that. So if it moves slower in this direction, they would come back and would not meet here and would make a dark spot, because if they come back at the same time, they both interfere constructively, just like when you took the wave section in Physical Science 20. When we have constructive interference, we have a maximum point happening. If we're talking about light interfering constructively, makes a bright spot. But if we have destructive interference or non-constructive arriving at different times, it'd be a darker fringe. Okay, so that's basically the apparatus there. And again, the video you'll see next shows that really, really well. So it's expected that if we orientate it differently, the ether medium, due to being orientated differently, would cause light to maybe go slower in one direction or faster, depending upon the orientation of the apparatus. For just as a boat has different speeds relative to the land when it moves upstream, downstream, or across the stream, so too light must do the same thing. But the weird thing that happened is that there is no difference at all. No matter how that apparatus was orientated, there was always a bright spot, indicating that both paths were identical in terms of speed and distance, and they came back, no matter how it was orientated. And that's a weird, weird conclusion. This is a great puzzle. A number of explanations were put forth over the years, but they led to contradictions or were otherwise generally not accepted. This null result was one of the great puzzles at the end of the 19th century. So really, no matter what reference frame, light travels at that speed. And there's some weird consequences as a result of that. Then in 1905, Albert Einstein proposed a radical new theory that reconciled these many problems in a simple way, but at the same time, as we shall see, it completely changed the ideas of space and time. So some of the highlights here, Earth is reference as an inertial reference frame. We assume it's at zero. And the medium for light waves cannot be air, since light travels from the sun to the earth merely with empty space, so it's that something else called ether. Since regular waves need a medium to travel, light therefore does too. But the result of that experiment, the weird thing that happens with that, when we look back here at the train example that we had, velocities add up when we're talking about regular speeds. But what that's implying is that if this guy were to shine a flashlight on the train, this guy would see the light beam move 3.00 times 10 to the 8 meters per second. Someone standing out here, and if he has shone the same flashlight, we would expect it to be, well, the speed of light plus the velocity of the train. But in reality, that experiment said that, nope, we don't add the velocity of the train on. The light is just simply 3.00 times 10 to the 8 meters per second. As weird as it sounds, that's what the experiment illustrated. Okay, We'll come back and go on to the next section in the next video. We'll see you again.